and I am recording. What we're going to be doing today, as I said in my invitation email, is we're going to talk about another integration technique. Okay, we've kind of gone from simple to complicated with integration. We started out with the power rule for integrating. That's kind of the basic one. We looked at basic rules for integrating, e to the x and ln of x, that sort of thing. What we then did was we moved on to slightly more complicated things where you've got kind of the remnants of taking the derivative of a composition. So you've got a function and what looks like part of its derivative multiplying it. Okay, so you're looking at a product of functions, but one looks like part of the derivative of the other. Okay, that's when we're going to use substitution. All right, and it's important to be able to recognize that. What we're going to be talking about today is yet a more complicated integrand thing we want to integrate. And that's where the two functions that are multiplied together are totally unrelated. Okay, so one is not the derivative of the other. They're just two separate families of functions. So we're going to use the strategy called integration by parts. And I'm going to show you how to do that with a table method. Okay, there's a couple of ways to show students how to do this. And personally, I like the table method because the table helps you keep track of all the bits that you're creating. Okay. So again, when you're doing calculus, the important thing with integration anyway, is to look carefully at what you have. Okay. And be able to recognize what you have. Okay. That A, it's a product, and B, how are the two functions that are multiplied together related to each other? Okay, you've got to be able to do that much algebra before you start with the calculus stuff. Okay, so I'm going to begin by sharing my browser with you, and I'll show you where we are in the course. Okay, we're currently in week 13. Okay, and we have 3.5a and b. They're not as tightly related as that numbering system might lead you to believe. A is integration by parts, which is what we're going to do today. And B is something called improper integrals. Okay, basically, these are definite integrals with one or more infinite bounds. Okay, and these actually have quite a few applications to business scenarios. Okay, particularly when you're talking about things continuing on into the indefinite future. Okay, say like rents or having to pay for pollution, that sort of thing. Okay, so what we're going to start with now is the integration by parts notes. You can see the assignments this week are just two homeworks, one on integration by parts, one on improper integrals. In the supplementary materials, I would like to point out this table of integrals, which I may refer to at some point. Okay, integration, as we said before, is a little harder than taking derivatives. And sometimes a table of integrals is just a cheat sheet. Okay, if your integral looks like this, here's a way you can integrate it. Just copy the pattern. Okay, it really is that simple. Okay, that's what a table of integrals is. And most multi-semester calculus books, like the big ones, okay, typically have tables of integrals in the back or the front. Okay, so you can refer to them. Okay, we don't have a massive textbook, so I put the table of integrals here, and it's also in your online notes and calculators module later on in the course. Okay, so I'm going to begin by opening the integration by parts notes. As always, if you've got comments, questions, or concerns as we move along, feel free to unmute yourself or type them in the chat. Okay, so just give me a moment. This takes me a minute or two. Alrighty, let me share this with you. Okay, so everybody should be seeing my notes, which says section 3.5a, integration by parts. Now, again, what I've done to create these notes for you is I've excerpted pieces from the text. And again, that doesn't mean you should, not read the text. You should read the text. Okay. But it's kind of hitting the highlights. Okay. So as I said in my introduction, okay, integration by parts is useful when the integrand is a pair of unrelated functions. Okay. In particular, one isn't part of the derivative of the other. Right? So if you see a quadratic function and a linear function multiplied together, you're thinking, hey, that linear looks like part of the derivative of the quadratic. So maybe I should use substitution, okay, as opposed to by parts, okay? That said, you can kind of use by parts in general, but it's got more steps, okay? It's a little bit more effort to do by parts, and it's also, because of the more steps, it's error prone. There's also, you'll see it when I show you the tabular method for doing integration by parts. There's a sign switch that happens regularly, and that sign switch is a source of error in your answer, okay? Like signs everywhere in algebra and calculus, okay? So essentially, it's as if the function we're interested in, our integrand, is a product of two functions, u and dv, okay? U is a function that's easy to differentiate, and dv is a function that's easy to integrate, okay? So the whole point behind integration by parts is to start out with a complicated integrand and then to turn it into something simpler, okay? So again, this is the way that most calculus teachers show integration by parts. Here's your given integral, okay? It's a product of the function u and dv. And when you integrate by parts, the first step is to multiply u and v together and then subtract the integral of v du, okay? Most students get lost with this, okay? But if you were to go, say, to tutoring in the LRC and a calculus tutor came up to you, she or he would probably show you this formula, okay? So I'm showing it to you so it looks familiar, okay? Now, I'm going to, like I said, I'm going to kind of reduce this formula into a table that's going to be easier to handle. Remember, I said u is the function we're going to differentiate. dv is the function we're going to integrate, okay? And then we're just going to pair them up in products from the table, okay? So one of the things you have to do when you decide to use integration by parts is to decide which function should be u and which function should be dv. That's the first thing you have to do. Well, the first thing you have to do is recognize you've got a product of functions, okay? But once you've done that, okay, then you have to choose, okay, which function is u, okay? So here's the rule of thumb they give you. When selecting the u for by parts, select a logarithmic expression if you've got one, like ln of x or log something of x. If you don't have that, select an algebraic expression, like x or dx or x squared, x cubed, okay? Basically a polynomial, okay? So basically, u should be a log or polynomial, okay? U should be a log or a polynomial function. And again, this is in order. Log first. If you don't have a log, then polynomial. Okay, so there's actually a more complicated rule than this, but I'm not going to share it because why complicate things? Okay. Okay, so the method I'm going to show you, a simpler method, is called the tabular method. Okay, so again, we're going to select which function is u based on this rule of thumb. and which the other function, of course, will be dv. Okay? We're going to set up a table with two columns like this, and we're going to say u over here, and we're going to say differentiate. Okay, and then we're going to say dv over here, and we're going to say integrate. Okay, so that's how we're going to start out our table. Sorry, just getting my stuff here. Okay, the idea then is to put your u function, copy the two functions, so u goes here and dv goes here from the integrand, and then you're going to keep differentiating u, right, as you go down. And the idea is we want to differentiate this till we get a 0, okay, or you determine the process will never give you a 0. Derivative will never be 0. Okay, and you're going to integrate dv going down this way. Okay, so we're going to do it that way. All right, so once you get u and dv, you decide on what they are and you put them in their respective columns in the table, then the process becomes a lot more mechanical. Okay, you just differentiate down the u column till you hit a 0 or till you realize, hey, you know what? This ain't ever going to be 0. I should just stop. Okay. And you go down the dv column, integrating each time you go down a row. Okay. Once you actually get done with this, again, this is a cookbook method. Okay, so I'm putting the steps here. Okay, so again, there's going to be stuff in each one of these, right? Okay, let's say you get a 0 here. Okay, in your differentiate column. You're going to create diagonal products this way. Okay, so these things in these cells are going to be multiplied together. And you're going to switch the signs on them. You're starting out with a plus, then a minus, then a plus, and so forth. Okay, and you pull them out, okay, in pairs. Let's say this is A, that's B, C, D, E, F, 0, and let's call this G. You pull out the products like this. You wind up with a positive A, D, right? Because the A and the D are on opposite sides of that line, and they're positive. Then you put a negative sign and you pull out CF, multiplying them together. And last, you put a positive sign and you pull out EG. Okay? So that's kind of an oversimplification of how we're going to do it. Okay? So that describes how to make the products, how to put the signs on the products. Okay? Now, one thing that can complicate this tabular method is when this column, the differentiate column, doesn't go to 0. In that case, you're going to just draw a horizontal line across and you're going to create an integral instead of a product. Okay, and I'll show you that when we get to the example. Okay, usually by the time you get down to a couple of rows in the table, the integral you're going to create by multiplying across here is a lot simpler than what you started with. Okay, so again, this seems, like I said, this seems awfully complicated, but it is actually pretty simple once you get the hang of it. Okay, so what we're going to do is show you a bunch of examples. Okay, all right, so let's take a look at example 1, and I'm going to ask you a question in the chat. What two functions, or I should say, what two types, families of functions are multiplied together, or two families of functions do you see multiplied here? Okay, what two families of functions are multiplied here? Okay, got to be able to do this part. Okay, unmute, type in the chat. By families of functions, I'm asking you log functions, polynomial functions, exponential functions, okay, that kind of thing. What two families do you see? Okay, Ni is saying linear function and exponential function. Okay, and remember, linear functions are polynomials. They're degree 1 polynomials. Okay, so they're a part of that family. Okay, so we have 10x. Okay, I'm going to call 10x an algebraic function. Remember their terminology for their rule of thumb. Algebraic essentially means polynomial. Exponential. Okay, got to be able to do that step. Okay, recognize you've got a product and then split it into two factors. Anybody questions on that part? Okay, believe it or not, that's the crucial part. Okay, so please ask if you've got questions. Yeah? No? Okay. Now, according to our rule of thumb, okay, that was on this previous page down here, it says, select a logarithmic expression if one is present. If not, select an algebraic expression. Okay, so I don't have a log expression here. So that means my algebraic expression is going to be my u. Okay, and by default, since the integrand is going to be conceived of u times dv, then the exponential is dv. By default, right? Once you pick u, dv is chosen. Okay, so then we're going to build our table. All right, and I'm going to basically say, here's u, which I'm going to differentiate. And here's dv, which I'm going to integrate. Again, I encourage you to write the words differentiate and integrate until you're comfortable with it. For a lot of you, seeing dv will remind you, oh, differential, I should integrate that because it's a rate. Okay, fine. Okay, but keep these words in there as long as you need them to tell you what you're doing. Okay, so u goes here. Here's 10x. And dv goes here, e to the 3x. Okay, I find it easier to differentiate my first column, okay, till it goes to 0 or until I realize, hey, it's not going to go to 0, okay, and then do the integration separately rather than going across in the row, because then you have to flip from differentiate to integrate. And I noticed, by the way, on exam 3, a fair number of you started differentiating in the middle of an integration problem. Okay, that is a really common thing for beginning calc students to do. Okay, and again, it's just a matter of staying focused on what the problem's asking for. Okay, all righty, so let's differentiate. If I differentiate 10x, that's 10x to the 1. That's 1 times 10 is 10. And then the x becomes x to the 0, which is just a 1. So the derivative of 10x is 10. Okay. If I differentiate again, starting with the 10, okay, 10's a constant. Okay, so that's going to give me a 0. Okay, stop when you get a 0. Okay. Okay, it's always a good idea to know what your stopping criterion is, and that's one of them. Okay, if that goes to 0. Now I'm going to go down my integrate column. Now remember, I'm integrating. Okay, Normally, okay, the integral of e to the 3x, if it was just e to the x, its integral would be e to the x, okay? But because I have this 3 up here, I have to remember to divide e to the 3x by the derivative of 3x. So e to the 3x over 3. Okay, if you were to differentiate this, you'd get 3e to the 3x over 3, which would just give you e to the 3x. Okay, remember, you can always reverse an antiderivative to see that you did it correctly, right? Now what I need to do is integrate this again, okay? What that's going to do is put another 3 down there in the denominator, okay? So this gives me e to the 3x over 9. Okay. And again, once I get the same number of elements, like the same number of rows filled, that's when I stop. Okay, so stop when opposite 0. Okay, so you don't have to keep integrating. You're just going to stop there. Okay. Now I need to form my products. Okay, remember how those work. They go diagonally from top left to bottom right. So there's one here, and there's one here. Okay, the first one starts out with a plus sign on it, and then the signs switch as you go down. So I only have 2 products that come out of here. So the first one's positive, the second one's negative. Now I'm just going to pull out the products. Okay, so the first one is 10x times e to the 3x over 3. Okay, see where those came from? Okay, I'll highlight, here's 10x. Here's e to the 3x over 3. Okay, see how that came out there? All right, and that's got a positive sign on it. So notice there's no leading sign, which implies it's positive. Okay. And then the next sign you would say would normally be a plus, but according to the table, it says that should be negative. Okay, that's this negative sign right here. The next product is going to be 10 times e to the 3x over 9. Okay, and again, just to show you those, here's the 10, and here's e to the 3x over 9. All right, and of course, since this was an indefinite integral, plus c. Okay, anything else you would do to this would be algebraically simplification. Okay, so you can algebraically simplify. Okay, I'm sure everybody can see that there's an e to the 3x and a 10 in every term. So at least I could factor that out if I wanted to. But this is where I want to make sure you get to. Okay, the integral is technically done once you're here. Okay, so I need some feedback from you. Okay, and I need to know, is the process clear to you? Okay, so please answer in the chat at least. Is it clear to you what I did? Okay, give me a yes or a no, please. Okay, yes, yes. Good. Okay, I'm getting a whole bunch of you, so that's awesome. Okay, so really, this is called the tabular method of integration by parts. Okay, the key thing is to know when to use it. Okay, and you use it when your integrand is a product of 2 unrelated functions. Like for example, here, okay, 10x is not part of the derivative of e to the 3x. Okay, e to the 3x would not give you an x as part of its derivative. It would just give you the constant 3. Okay, so that's what's important to realize. You can see how you need to be comfortable enough with derivatives to be able to tell what you've got here. Okay, and I'd encourage you to print off your derivative cheat sheet and have it handy, at least while you're starting to learn how to do this. Okay, let's take a look at some more of these. Okay, now again, I have something that's in the denominator of a fraction here. So I'm going to start out by rewriting this as a product. Okay, everybody see what I did there? I took e to the minus 5x out of the denominator and I made its exponent negative. Okay, that tells you that it belongs in the denominator of a fraction. Why did I do that? Because it's a lot easier to deal with products and exponents than it is with fractions. Okay, so again, tell me what two functions I have here, what two kinds of functions. Okay, so tell me what these two types of functions are. Okay, everybody see polynomial and exponential. Okay, good, me. Okay, polynomial is the x, and e to the minus 5x is exponential. And again, we're calling x algebraic. And we're going to call e to the minus 5x exponential. Again, it's just that rule of thumb that's letting us call x an algebraic function. Just think of it as polynomials. Okay, linears are polynomials. Okay, so that means, again, x is going to be u, and e to the minus 5x is going to be dv by the rule of thumb. Okay, so I'm going to build my table. And then I'm going to put in u differentiate. And dv integrate. Okay, and again, my x goes here, and my e to the minus 5x goes here. Okay. If I differentiate x to the first, I'm going to get a 1. Okay, where'd the 1 come from? Well, it's x to the first, so bring down the 1 and drop the exponent by 1. That gives you 1 times x to the 0. X to the 0 is 1, so you have 1 times 1. Okay, and 1's a constant, so when I differentiate it a second time, I get a 0. Okay, and this is my stopping condition. Okay. Going down the integrate side, I'm going to do it exactly like the last time, where that negative 5 that's up in the exponent is going to wind up in the denominator. Okay, so if I were to differentiate this back, I get negative 5 e to the negative 5x over negative 5. The negative 5's cancel, and I get e to the negative 5x back. Okay. Again, what you're seeing here is the result of the chain rule, okay, when you're doing derivatives here. Okay. Now, here's the trick. Okay, if I integrate this again, here's what happens. There's a negative 5 down here, and I'm going to multiply it by another negative 5. Okay, so with this integral, the signs change. This is now a positive 25. Okay, so notice this is a negative 5, so this whole fraction's negative. Okay, so the signs are flipping. Okay, if it disturbs you to pull the negative sign out in front of the fraction, leave it in the denominator, okay? But that's going to affect things when you make the products. Okay, again, I'm going to stop on the integration column when I get to the 0 row, and then I'm going to make my products. Again, I'm going to wind up with two products. First one's positive, second one's negative. And then I'm just going to pull out the products. Okay, so that's going to be x times e to the minus 5x over minus 5. Okay, the second one has a minus sign in front of it, and that's 1 times e to the 5x over 25. Okay, and everybody hopefully can see the components. Here's the x. Okay, here's the e to the negative 5x over negative 5. Here's the 1, which technically you don't need to write. And here's the other one. Okay. And again, don't forget, it's an indefinite integral, so plus c. Okay, questions so far? Questions so far? How are we doing? None from you? Okay, good. Anybody else? Questions? Okay, you can see, again, as long as you can reliably do the differentiation and the integration, this is super easy. Okay. Now let's take a look at this one. Okay. What two types of functions are here? What two types of functions are multiplied in example 3? Okay. Yes. Okay. We have a polynomial, which is x cubed. Okay. Which again, I'm going to call algebraic. And then I have ln 5x, which is a log function, obviously. Now, if you go back to your rule of thumb, okay, over here, the rule of thumb says when selecting u, select a log function if you have one. Okay, so I have a log and an algebraic, and they're telling me select the log function as u. All right, so again, this is going to be u, this is going to be dv. Again, the way I'm doing that is strictly with this rule of thumb. Okay. All right, so then I'm going to make my table. Right, this one will be a little bit different. Okay, so differentiate. Put u first. U, and this is differentiate. And then dv is integrate. Okay, so I chose u to be the ln 5x, so that goes here. Okay, you have to remember how to differentiate a log function. Okay. All right, and I'm going to integrate x cubed. That's my dv. Okay, now I'll tell you right away, okay, that what'll happen, okay, is when you differentiate ln, okay, it's never going to go to 0. Okay, let me remind you how you differentiate this. Okay, the derivative of ln of x is 1 over x. Okay, now ln of 5x is 1 over the argument. Okay, so the argument to ln here is 5x. And then because the argument is actually a function of x, you have to use the chain rule. Okay, you have to multiply by the derivative of 5x. Well, that's just 5. Okay, so that's the chain rule. Okay, the 1 over 5x is the derivative of the outer function, ln 5x. And then you're multiplying that by the derivative of the inner function, which is the argument, and that's just a 5. I think you can see these cancel out, right? So my derivative is going to be 1 over x. Okay, it's an interesting feature of taking a derivative of ln of some number times x. ln of 6x is also 1 over x. ln of 8x is also 1 over x, okay? Because of this feature that happens with the chain rule, okay? Now, if I differentiate this again, okay, it's no longer a log function, it's x to the minus 1, okay? And if I differentiate that with respect to x, what happens? I get -1. I'm using the power rule. Bring down the exponent, subtract 1 from the exponent. So this becomes -x to the minus 2, okay, which is 1 over x to the 2. I think you can see if I keep doing this, I'm going to wind up getting -2 times negative. So I'm going to get 2 times x to the minus 3. Okay. Then I'm going to get -6 times x to the minus 4. Okay. It's a pattern that's going to keep going. Okay. So this will never be 0. Okay. And that's going to happen every time you have a log function. Okay. You're not ever going to get that to become 0. Okay. So stop. Okay, no sense keeping on. You'll be doing it the rest of your life. Okay. Now let's go down our integrate column. Now remember, we're integrating, we're not differentiating. Okay. So the rule says add 1 to the exponent, put the answer over the new exponent. Okay. And we need to integrate this one more time to match up here. Okay. All right. Now we would normally, okay, but basically I just stopped here, okay, to let you know that this will never become 0. Okay. So again, we don't need to integrate one more time. We're going to stop here. Okay. I basically just did this one more time to show you that this will never become 0. Technically, you'd be able to tell at this point when you had 1 over x. Well, if I keep differentiating it, I'm just going to keep getting derivatives with larger and larger exponents in the denominator. Okay, so you could stop here. I just stopped you here to show you the pattern. Okay. All right, so as soon as you know that you're not going to ever get 0, stop. Okay, and then you've got one product that goes like this. Okay, and then you've got another product that's going to go like this, but this will be an integral. Right, and the signs are the same, plus on this one, minus on this one. Okay, so let me pull out the products here so you can see. Okay, so the first one is ln 5x times x to the 4th over 4, and it's positive. And again, here's the ln 5x. Here's the x to the 4 over 4, just so you can see where they are. Okay, now I have a minus sign on my next term. And then an integral. Okay, that's because I'm going sideways across. I'm not going diagonally. Okay. And then I have the product inside the integral. Okay, there's my product. Okay, so here's the 1 over x. And again, I'm going to just put a double shading over here. Okay, so I'm copying the same thing. All right, now remember, since it's an integral, you're going to need a dx here. Okay, so you're just making a product, and instead of diagonally down the table, you're going straight horizontally across. Okay. Now, again, this part's done. I don't need to look at it. But before I try to integrate, look at the integrand. Okay, can you simplify the integrand? The new integrand. Is there anything we can do to simplify this? Anybody see something we can simplify here? Okay, somebody saying yes. Okay, anybody else see what we can do here? Okay, notice you've got an x to the first in the denominator and an x to the fourth in the numerator. Okay, so you can divide out a power of x. All right, I'm just going to rewrite this without the highlighting. And then I'm going to simplify this. Okay, everybody see that x goes into x once and it goes into x to the fourth 3 times. Okay, so this becomes x to the third over 4 dx. Okay, and that can also be rewritten like this. Okay, minus 1/4, oops. Okay, everybody all right with that? Remember we said dividing by 4 is the same as multiplying by 1/4. Why would I want to rewrite it that way? So I can pull the 1/4 right through the integral sign. Okay, now I have an integral that's super, super easy to do. Okay, this is a real simple integral. I just used the power rule. Okay, and that gives me this. I'm going to copy the whole part of the integral that I wrote down already so I don't lose it. Okay, and then the integral of x cubed dx is x to the fourth over 4 plus c. Okay, so again, you can see this integrates to x to the fourth over 4 plus c. And then you can just multiply the 1/4 that was outside by the 4 that's dividing. So you have ln 5x times x to the 4 over 4 minus x to the 4 over 16. Okay. Everybody okay with example 3? Okay, so questions on example 3. Okay, example 3 shows you when you've got logs, how you have to basically stop the process prematurely and then pull out an integral by going across the table. Okay, that'll only happen when you have logs. Okay, so again, you can see though, because the derivative of log is 1 over x, you usually wind up canceling out a power of x, and it makes the integral really easy to do. Okay, much easier than what we started with. Any questions on the algebra in this problem? Anybody questions on the algebra? Okay, no questions. If we know the log won't be 0, why do we choose it for the u? Okay, it's basically the rule of thumb. Okay, it's easier to differentiate, okay, than the other function, than to integrate. Okay, it's purely the rule of thumb. Okay, it basically makes it easier to work. Okay, so the rule of thumb is the one thing that I had on the first page of the notes over here. Okay, it says when you're trying to choose u for by parts, select a log expression if you have one. Okay, otherwise pick a polynomial, which they call algebraic. Okay, and again, they do it just to make the process work out easily. Okay, again, the whole point of this is to kind of simplify things. Okay, why would we multiply x to the whole? Okay, the 1/4 was what we pulled through the integration. Okay, remember that was multiplying my x cubed. So I pulled it through the integral, and now it's sitting out there. Okay, so when you integrate x cubed, you get x to the 4th over 4, but that 1/4 is still multiplying it. Okay, so that's where that extra 1/4 came from. And you notice the 4 times 4 is in the denominators. Okay, so 4 times 4 denominator gives 16. Okay, yeah. Again, it's real easy. Take it from me. It's real easy when you're doing calculus and you pull through constants, coefficients like this. They're not constants. They're multiplying whatever term was in here. Okay, remember this started out as x cubed over 4. I rewrote that as 1/4 of x cubed, so I could pull through the coefficient. Okay, it's a real common error to lose those. Okay, to just forget about them. Don't forget about them. Okay, that's why I wrote it down before I did the integration. Okay, it's exactly like, you know, doing accounting. If you put stuff in the wrong place or you forget to write it down, you've got the wrong answer. Okay, it's no more complicated than that. Okay, it's a case of just keep track. Okay. All right. Let's show, I'm going to show you a weird one. Okay, so ready for a weird one. Okay, ready for a weird one. Okay, let me show you this one. Okay. And again, usually I show you these because you're probably going to see them in homework, just saying. Okay, so it might be a good idea to kind of make a note. Take a look at these two functions. Okay, what types of functions are these two? Anybody have any thoughts? Yeah, I got a linear and a linear raised to a power. Okay, so these are both algebraic functions. Okay, and you should be looking at this 5x plus 1 and saying, if I differentiate this, I'm just going to get a 5. So what do I do with the extra x? So you might be thinking, could I use substitution instead? Okay, I'm not seeing two totally unrelated types of functions. They're both the same kind. Okay, and if you look at this, quickly, you'd say, well, X is not part of the derivative of 5x plus 1. Okay, but it turns out that yes, you can use substitution. Okay, so let me show you how. Okay, if you might remember, for substitution, you're going to pick your u value, the thing you're substituting for, to be any quantity in parentheses, any quantity in a denominator, which you could write as something in parentheses to a negative power, or an exponent on e. Right? So remember, u substitution choose u to be quantity in parentheses, quantity in denominator, which then you're going to write as a quantity in parentheses with a negative exponent, quantity in exponent. Okay, so basically these are your kind of rules of thumb for using substitution. So that tells me I'm going to let u be 5x plus 1. Okay, let u be 5x plus 1. I'm going to do my usual du over dx. Okay, now I'm never going to get an x out of this. Okay, but I'm trying to match just the dx. Okay, so du over dx is 5, right? The derivative of u with respect to x is just the 5. Now I'm going to try to get dx alone. Sorry. Okay, so I'm going to multiply both sides by dx. Okay, that cancels out on the left. I get du equals 5 dx, and then all I have to do to get dx alone, divide by 5, which of course I'm going to write as 1/5 du equals dx, right? Those cancel out. Everybody remember that process? Oh, I wish I could spell remember. Everybody remember that process? Okay, substitution. Remember, the integrals just come at you in the wild. They don't just show up in the chapter on substitution or the chapter on integration by parts. You have to make the decision. Okay, so that's great. So far we have dx is 1/5 du. That's good. Okay, and we have this part is going to be u. Okay, but we still have a problem. We have x. Okay, everybody see the problem? Okay, now here's where the insight comes in. See this equation that you have that says u equals 5x plus 1? You can solve that for x. Okay, so the first thing I'm going to do is subtract 1 from both sides. That gives me u minus 1 is 5x. All I did was subtract the 1 here and subtract the 1 here. And then I'm going to divide both sides by 5. So I get u minus 1 over 5 equals x. Okay, now I have something I could substitute in for x, right? Everybody okay with that? So now I have bits that match all the parts of my integral. Everybody good with it so far? Okay. All righty. So now let's do the substitution part. So here's the integral. Okay, my x is going to be u minus 1 over 5. Okay, so that's x. And then I have u to the 19th Okay, and that's just substituting for u. Okay. And then the last bit is the 1/5 du. Okay, so that's 1/5 du. That's this part. Okay, that's the dx. Everybody all right with the substitution? Okay. Now here's what you've got to do. You got to look at this and you've got to do some algebra on it first. First, I'm going to get rid of my coefficients. Okay, so this is going to be 1/5 times u minus 1 times u to the 19th times 1/5 du. Okay, so see these two? I'm going to multiply them and I'm going to pull them through the integral. 1/25 u minus 1 u to the 19th du. Everybody see what I did there? See how I pulled the coefficients through? Okay. Whenever you've got this divide by something, write it as multiplying by the reciprocal. Okay. So these came through there. Everything here is multiplied. So I can multiply 1/5 times 1/5 to get 1/25. Okay. Now you should be able to see all I have to do is distribute u to the 19th, right? And that's going to give me the integral of u to the 20th minus u to the 19th, oops, times du. Okay, just distributing u to the 19th to both things in parentheses. Okay, now this becomes easy to integrate with the power rule. Okay, this is u to the 21st over 21 minus u to the 20th over 20 plus c. All right, and then all I have to do is substitute back my x term. All right, so this gives me 5x plus 1 to the 21st over 21 minus 5x plus 1 to the 20th over 20. Okay, so again, this required a little extra thought. Okay. And again, this is an example of using substitution in a way that kind of extends what you did with it before. I mean, we started it out the same way. We picked a u, and then we matched the other part, one other part of the integrand by doing du over dx. Okay. But the extra piece, the piece that was the insight, was this. Okay. To realize that you could solve your u equals expression or equation for x. Okay, and then you're able to match that extra part. Okay, like I said, integration can be tricky. Integration can be tricky. Okay, so sometimes it requires some insight like this. Right? Anybody questions on 4? Questions on example 4? Okay. So needless to say, this strategy can also be used to evaluate definite integrals. Okay. for example, if I have this sort of situation, you can see I have bounds or limits on my integral. Okay, so that means this is going to give me a number. Not a function. Okay, so basically that's because it's a definite integral. I'll need to use the fundamental theorem of calculus, okay, to actually get the number out of this. But first, if you look at it, you can rewrite this as a product by just bringing that x squared, okay, up like this. You could say ln x times x to the minus 2 dx. Okay, so again, I have a single term in my denominator. Whenever you have that, you can always rewrite it with a negative exponent and create a product out of a quotient. Don't have any quotient rule for integration. Okay, so try to make products out of the integrands. Okay, there are two rules for integrating products, one substitution and one is by parts. Now, if you look at this, okay, x to the minus 2 is not part of the derivative of ln of x. ln of x is not part of the derivative of x to the minus 2. So I'm stuck with using by parts. Okay, I'm seeing a product of unrelated functions. And again, what family of functions do we have? I have a log function, which is ln x, and I have an algebraic function, x to the minus 2. Okay, I know it's not technically a polynomial, but it would be a polynomial in a denominator. Okay, algebraic. Okay, so according to my rule of thumb, ln of x will be u, and this will be dv. Okay, all right, so build my table. Okay, now remember, since my u value is the log function, this is going to not ever give me a 0. Okay, so here's u. Differentiate my u and integrate my dv. Okay, so I'm going to do the antiderivative stuff first. Then I'm going to use the fundamental theorem on my antiderivative to give me my number that I'm looking for. Okay, so let's put ln of x here. Now, again, if I differentiate this, I get 1 over x. And I know from before, as soon as I get this, stop. Okay, it will never equal 0. Okay, so I know that from my previous example. Okay, my dv is x to the minus 2. Right, and I'm integrating this. Okay, so remember, integration involves adding 1 to the exponent and putting your result over your new exponent. Okay, so this is negative 2 minus 1 is x to the minus 1 over minus 1. Okay. And again, since I'm stopping at this row, I'm stopping the whole process here. Here's my first product, which has a plus sign on it. And since, again, I stopped it before it went to 0, this is going to be an integral. Okay, that way. All right. Please realize that this can be rewritten as negative 1 over x, just so you see it. Okay. You've got to kind of do algebra at the same time you're doing some calculus here. So now let's pull out the products. Okay, so my first product is going to be ln of x times negative 1 over x. right? Just so everybody can see it. Okay, and my second product is going to be going diagonally across. So 1 over x times negative 1 over x. And it's got a minus sign, okay, and an integral. Okay, so the minus sign in front of the integral is this minus sign from the table. And then I'm going to multiply these two highlighted things together. So 1 over x times negative 1 over x. And it's an integral, so dx. And again, just highlighting it so you can see where they're coming from. Okay. Everybody all right with that part? Okay. Now, I think you can see that if I multiply these two together, I'm going to get negative 1 over x squared dx. Okay. Notice what I'm doing with the negative sign. See this negative sign on the 1 over x? This is multiplying ln of x, so I could pull that negative sign out in front of the product. Okay. Here, I had a negative sign inside the integrand, and I also have one outside. What's the effect of that? Well, the effect of that is to turn this into a plus. Okay. All right, so I'm just doing some algebra here. Okay, I'm going to come up over here. So I have ln x times 1 over x, and there's a minus sign out in front. Okay, now this has become a plus. Okay, in preparation for integrating, I'm going to write this as x to the minus 2 dx. I just did a bunch of algebra to get rid of all the clutter, right? These double negative signs, okay? I said minus a minus is the same as a plus. Okay, that's all I did here. Okay, and now I'm just rewriting 1 over x squared as x to the minus 2. And then integrating that, this part I'm just copying. Okay, this says add 1 to the exponent. Put your answer over the new exponent. Okay, so minus ln x times 1 over x. This is going to give me a negative 1 down here and a negative 1 up here. So plus x to the minus 1 over minus 1. And again, playing with the signs. Okay, plus a negative fraction would give me minus 1 over x. Okay, this minus in front came from the minus 1 down here, and then the minus 1 on the exponent flips x, okay, into the denominator. And then we're going to evaluate this from 1 to 2, which were the bounds on the original integral. Again, this is something that you can do, again, on a calculator. Okay, you can do that on the calculator. All right, and when I did that, I got approximately 0.1534. Okay, most of the work here, though, is doing the antiderivative. Okay, so again, once this is the more complicated case when you've got another integral to do. But again, please, please be comfortable enough with the algebra that you can massage the second integral that comes out of this. Okay, this type of problem is mainly algebra. Okay, is mainly algebra. Everybody okay with it? Okay. Questions? Okay, I want to take the remainder of the time, if you don't have questions, to look at tables of integrals. And I might just do one or so problems on this. Depends on how many questions you have. Is everybody all right with again, the definite integral? It's exactly like doing an antiderivative. And then at the very last step, once you get your antiderivative, you just use the fundamental theorem, right, to evaluate it. So you evaluate this at 2, and then you subtract the value at 1. Okay? All right, not seeing questions. Again, I'm kind of waiting to see if anybody is confused about anything. All right, well, the last topic is using these tables. Okay, so again, this is an understatement. There are many integration techniques we're not going to be studying. Why? Because they typically don't show up in business type problems. Okay, most of the complicated integral type things show up in physics and engineering type of problems. Okay, and so we're not terribly interested in those in this class. Okay, so people have noticed these patterns and they've created formulas into what they call tables of integrals. Okay, a general cheat sheet for integration. Okay, and again, there's one in the supplemental materials of this week in Canvas. So here are 2 types of entries you might find. Okay, if you have an integrand that looks like 1 over x squared minus some quantity squared, okay, it integrates like this. They're just telling you, skip the integration step, just follow the pattern. Okay, likewise, if you have an integrand that's 1 over the square root of the sum of 2 squares, where one of them is x squared, here's what it integrates like. Don't waste your time. Okay, so this is simply pattern matching. Okay, and A is a number, not a variable. Okay, A is a number, right? Just match the pattern. Okay, so here's an example of how you might use that. Okay, you're taking a look at this integral. It looks very similar to the first pattern, right? My integrand is a number over x squared minus something that's a perfect square. Okay, 3 squared is 9. So A equals 3 here. Okay, everybody see that? You can better see the match. Okay, and we can pull this 5 right through the integral. Okay, so let me rewrite this like this. Okay, so you can see that 9 is 3 squared. The first thing I'm going to do is pull my 5 through the integral sign. This is 5 times 1, right? So 5 comes through, and now this is 1 over x squared minus 3 squared dx. Okay, why did I do that? Because now I have an exact match to the pattern in the table. Okay, so here I have, again, just so we're clear, okay, A equals 3 here. All right, and this is going to integrate to, again, keeping the pattern. I'll just write the pattern, 1 over 2a times ln x minus a over x plus a plus c. Okay, so see what I'm doing? I'm just copying the pattern exactly from the table of integrals. Okay, 1 over 2a ln x minus a over x plus a, take the absolute value because I can't feed negative things to log, plus c. And then all I have to do is say, oh, well, that's right. A is 3. So everywhere I see an A, I'm going to put in a 3. Right? So this is going to be 2 times 3. Okay. And again, simplifying further, this is going to be 5/6, right? 5 in the numerator, 6 in the denominator. ln x minus 3, x plus 3, plus c. All I had to do was a little algebra. I didn't have to do any calculus. Okay, see, I use the pattern. Anybody questions on how I use the pattern? Anybody see questions? Okay, again, it's difficult for me to get these both. Try to shrink this a little so I can show you both at the same time. I'm matching this pattern up here. And again, it's just a matter of identify that you have a match to the pattern and then pick out what your A is. Okay. Just one more that's slightly more complicated, and I'll show you how this works. Okay. Well, I'm looking at this and I'm seeing, well, geez, I'm seeing a square root here. Okay. But the powers are wrong. Okay. There's an x squared in the numerator. Okay. That doesn't match. Okay. But I'm aiming for this rule right here. Okay. So how do I fix things? I'm going to try to rewrite the denominator to look like something squared. Okay, so here's what I'm thinking. X to the 6 minus 16 can be written like this. And this is using properties of exponents. Well, how would I write it as something squared? How about x cubed squared? Right? Remember, when you raise a power to a power, you multiply your exponents. Okay, and then of course, this is 16 is 4 squared. Okay, then what you have to notice is I'm sorry, say again.
¿A las 11?
Did you have a question? Do you have a question?
Oh, no, sorry.
Oh, no worries. Okay. All right. So what you want to notice is that x squared in the numerator of my integrand is the derivative of x cubed. Okay. All right. So I'm going to let u equals x cubed. Du over dx is going to be 3x squared. Okay, and again, I'm trying to get x squared dx. Okay, this is what I'm trying to match. Okay, I already have the x squared, so let me get the dx on that side. I'll multiply both sides by dx. And then the only thing I need to do is divide by 3 here. So I have 1/3 du equals x squared dx, which is now a match, okay, for that part of the integral. All right. So what I'm going to do here is let u be x cubed. Okay. So then I can rewrite my integral like this. Okay. I have, okay, this is u, which is x cubed squared, right? Here's u in here. U is x cubed. So u squared would be x to the 6th. Okay, I have a 1 up here. And then 1/3 du is the dx. All right, so again, I want to make sure everybody understands, again, u is x cubed. Okay, so u to the 6th is x squared. So that's how I substituted for x to the 6th. Okay, I'm going to pull through the 1/3. And now I have an exact match for my pattern. This is a plus, minus rather, I'm sorry. Okay. Again, there should be a plus, not a minus. That's where I'm getting confused. Okay, in the example, I have a plus sign, you have a minus. So this should be a plus all the way down to match the pattern. Okay, there's a plus sign between the x to the 6th and the 16. Okay, so I haven't changed anything yet. Okay, I just am fixing a typo in the original problem. And I'm showing you this is a plus, this is a plus, this is a plus. Okay, now this much matches the pattern. Okay, and if I integrate this here, okay, this is going to give me, according to the pattern, where's the bat? I want to show you the pattern again. Okay, ln, this is going to be u plus u squared plus a squared plus c. Okay, so this will integrate to 1/3 ln absolute value u plus u squared plus 4 squared plus c. That's the pattern right here from the table. And then all you need to do is plug your u back. So what I had to do was I had to realize that I could write x to the 6th as x cubed squared, and then I had to use substitution. Okay, so use substitution. So this was a combination of using substitution and an integral table. All right, here's the final answer with your u going back in as x cubed. Again, x cubed squared is x to the 6th. All right, so here's the final answer. So again, why am I showing you this kind of complicated example? Just to show you that you can use a combination of techniques. You can use an integral table as well as substitution. What made me realize I needed to use substitution? The x squared in the numerator, okay? Once I got u equals x cubed, I said, okay, well, the derivative of that is x squared. That's going to give me, okay, the x squared I need. Okay, so questions on this example? Any questions on this example? Again, this is kind of a mix of techniques. Okay, anybody questions? So again, when you do integration, please take a couple of minutes to stare at your integrand and like work ahead a step or two to see what is it I have, what's my best strategy, okay? This is a weird enough integrand. I would look it up in a table of integrals. And then once I would do that, I'd realize, hey, you know what? The powers don't match. So maybe I need to do substitution as well. Okay, because I might have part of the derivative of this thing. Okay. Yes. No, I didn't take the derivative of it. X squared is the derivative of u equals x. It's part of the. Okay, it's part of the derivative of u. Okay, so I used substitution. Okay, you can see that right here where I did du dx, it gave me 3x squared. And then I got x squared dx, this highlighted yellow bit in the integrand. I isolated that. Okay, so that's what made me use substitution, was that x squared up in the derivative, in the numerator. Okay, any other questions? Other questions or additional questions? No? Okay, well, I'm going to stop sharing and come back to the meeting. Okay, and again, just in case you weren't here at the beginning, okay, please take a look at your exam 3, which I've uploaded to the exam 3 assignment in Canvas. You can see my comments in there. You can see correct answers in there. And again, please look at your adjusted score and let me know if you've got questions on anything. But as far as integration by parts, any general integration by parts questions? Anybody has any general questions about integration by parts? What we did today?